So here's another example on optimization, and take some time to look at it, and we'll discuss the solution. So given the perimeter equals 200 meters, what equation can we set up for 200? Okay, the perimeter consists of 2x. This is the perimeter of the entire track. So it consists of these two lines, each side was x, and also these two half circles on either end. That really makes up a whole circle, doesn't it? So what is the circumference of the whole circle? 2 pi r. So the perimeter of this track consists of 2x plus 2 pi r, correct? That should be equal to 200. That's given. We're going to maximize the rectangular portion of this track. So we want to maximize area, but just tell me the area of the rectangular portion. Exactly. Basically, this is a rectangle. One side is x, one side is 2r, right? So the area is 2r times x. Any questions so far? This is the one we're going to write in one variable. This is the one we're going to differentiate, right? So we need to get rid of one of those variables. Which one would you like to get rid of? You really have a choice. I'm going to solve for x in the first equation. You could have just as easily solved for r. Okay, so if you like to do it differently, and we can check our answers at the end. I'm going to take that first equation and solve for x. So 200 equals 2x plus 2 pi r. So 2x equals 200 minus 2 pi r. And what about x? Divide everything by 2, right? Can you tell me that in simple form? 100 minus pi r. Basically, if we divide the entire right-hand side by 2, each term will be divided by 2, and this is what you will have. Okay, now that we have our x, we can go back to area function and accomplish our job of getting it in one variable. Any questions so far? Okay, so 2rx. R is still there. Instead of x, I'm going to substitute 100 minus pi r. Okay, then what should I do? Distribute. Now, many times you come this far, you say, okay, I've done a lot of work, let me go ahead and set this equal to 0. But we need to go one more step before we set it equal to 0, right? What is that other step? Differentiate. Because why are we setting the derivative equal to 0? Remember, if this is like your area function, let's say, for any function, when you set the derivative equal to 0, you're finding points where slope is 0. That those are the candidates to be maximums and minimums, right? That's why we need to get the derivative first. The derivative is 200 minus 4 pi r, and then we set that equal to 0. So if you solve that equation for r, you will get 200 over 4 pi and you can simplify this a little bit. 200 over 4 is 50. If you want, you can write it like this, 50 divided by pi. Or just as easily, you could have gotten a decimal answer. And what is 50 over pi as a decimal? 15.9. And everything was in terms of meters. Yeah, so that would be roughly 15.9 meters. But I noticed that if I look into the equation for x over here, I noticed r will be multiplied by pi anyway. So I'm not going to simplify it yet, because when I plug it in there, I can simplify this at the end. So x is equal to, from this equation, 100 minus pi times r, where r is 50 over pi. Again, you could have used a decimal answer. That's fine with me. Your answers are just going to be slightly different due to rounding. So now the pi's cancel. 100 minus 50 is 50. So we're saying the dimensions are x is 50 and r is 50 over pi, in other words, 15.9 meters. And let me just do my quick checking here. I'm going to look at the second derivative of this function. What is the second derivative of this function? Negative 4 pi. Doesn't even have an r in it, nothing to plug in. This is always, always negative, right? Therefore, it's always concave down. The point we found is certainly going to be a maximum for this function. So 50 for x. So 15.9 is like almost 16, let's say. So if you want to just visualize how this track is going to look like, so it's like 50 on this side, 50 on this side, and this side should be 2r, right? The width should be 2r, and roughly 32 meters on that side. So 50 on either side, and the other side will be roughly 32, because 2 times 16 is roughly 32. Okay. So I'd like, first of all, for you to read the question. Perhaps try to write down some equations down, and then we're going to discuss it in just a few moments. But I want you to be familiar with the question before we start discussing it. So I'm going to pause this. And I guess the point A is right at the origin right here. I should also mark that point. Okay, so for this question, we're trying to minimize the total cost of laying the cable, right? Basically, basically this is your underwater, right? And this is your overland portion. And as we discussed, you can go straight down the coast directly to A and then move to B, or you can try to go all underground directly to B, or you land somewhere in the middle there, somewhere in between A and B at a point P. We're trying to decide where should the point P, so the total cost of laying the cable is minimized. All right. So we're trying to minimize the cost function. I think everybody would agree with that. So we're going to minimize the cost function. I'm going to write it as a function of x. Okay, could anybody tell me, based on this picture, what will be the cost of laying cable underground in this blue region, about over the blue line there? Cost is $1 million per kilometer when it's underwater. And how long is that line? That's the question. That's the hypotenuse of this triangle, right? So there's the square root of 5 squared plus x squared. In other words, 25 plus x squared. That is the length of that cable. And we know that because they said that this, let's see, the oil well, it was 5 kilometers offshore. So we knew that that distance was 5 kilometers. So what is the cost of laying the cable over that distance? It's $1 million per kilometer, and it's that length. What is the cost of laying it over that distance? Exactly. However many kilometers this is, you multiply it by 1 million. That's your total cost of laying the cable in that, over that under the ground and over the blue region. So 1 million times the square root of 25 plus x squared. Plus, then you're going to lay the cable over above land, so over here, the red region. And here I show you the length of that. Some questions, all they're going to tell you is they're going to tell, okay, this distance is 8 kilometers. So you decide that this distance will be x. Then what will be the remaining distance there, that the part that you go above the ground? That's 8 minus x. And what is the price of laying cable over that red line? 500,000. That's cheaper. So 500,000, let me get a comma there, 500,000 times the distance in red, which is 8 minus x. The remaining way is going to be laid over the ground. The red region is above the water. This is like the highway. This line represents the highway, whereas this is water here. So laying over the blue line, you're laying under the water. So the blue line represents the water, and the red line represents over on the ground. Okay, do I need to replace anything here? I have the cost equation. Do I need to maximize, minimize? What do I need to do to this? You want the lowest possible cost, right? So you want to minimize the cost. Minimize the cost. Do I need to get rid of any variables here? Already I have only one variable, so that we're in good shape there. But you know, what I'm going to do here to simplify it a little bit, I'm going to factor out 500,000. That's going to make things a lot easier. And let's just say 500,000. I'm going to call it 500K for short. What is left inside? 2 times the square root of 25 plus x squared, and then plus, if you pull out 500,000 from the red terms, what do you get? Just 8 minus x. Okay, what should I be doing next? So you're thinking about differentiation. So you're already looking ahead, writing it as an exponent, like the square root means to the 1/2 power. Would everybody agree? Should we be differentiating this right now? Because if you want to find maximums or minimums, you want to set the derivative equal to 0, right? So we need to differentiate this messy looking function. So let's do it. So let's find c prime, the derivative of this function. Okay, here you have a constant times a function. This is your constant. When you have a constant times a function, you can leave the constant as it is. This is 500,000, which I abbreviate as 500K. Yes, when you're going inside, you're going to need a chain rule. Exactly. How are we going to differentiate 2 times the square root of 25 plus x squared? The 2 still remains, right? Let's just differentiate. I'm going to do it on the side here. 25 plus x squared to the 1/2 power. This is what we want to differentiate, right? So what should I be doing first to differentiate that? Bring the 1/2 down. Then raise it to which power? To negative 1/2 power, because we subtract 1, right? And then multiply everything. As Ryan suggested, he said, let's use a chain rule, right? We should multiply everything by what? The derivative of the inside, which is 2x. That takes care of this term, derivative of this term. Derivative of 8 is 0. What about derivative of negative x? Negative 1. So let's make sure we put that in there as well. So minus 1. And do you see cancellation about the 2's? Like this 2 and 1/2, we can get rid of them right away, right? And the negative 1/2 power, can I put it on the bottom? How can I put it on the bottom? As a square root, right? That's going to be on the bottom, a square root expression. So let's clean it up a little bit before we set it equal to 0. Let's try to clean it up. So c prime is equal to 500,000 or 500K times, in parentheses, the 2's already canceled, right? I have a 2x on the top, and on the bottom, the square root of 25 plus x squared. I'm not done yet. So the next term, minus 1. Did I miss anything? Any questions? Oh, you see, this term was only belonging to the first term, right? The negative 1 on the second part was independent of that. Minus 1 is just all by itself, so I just carried the minus 1 right down there. No, we cannot write it like that. No, the question is, can I write it like this, 2x minus 1 over the big square root? No, because this negative 1 did not have a square root on the bottom in the expression. I got to keep it just as it was. Okay. So now I'm ready to set it equal to 0. right away the 500,000 disappears, right? We're going to divide both sides by that. Done. We don't need to carry out that extra number all the way in the next few steps. So let me just write the cleaner equation then, the simpler equation. 2x over root 25 plus x squared. And instead of saying minus 1 equal to 0, what could I say? This is equal to what? 1. I divided both sides, yes. Got rid of that. How can I solve for x in this equation? Looks very different than all the other equations we've dealt with so far. Excuse me. We could cross multiply, yes. Let's try it. 2x is equal to 1 times the square root of 25 plus x squared. We can't do that. If you have root a times b, you can split it into root a times root b. But if there's a plus, you cannot simplify it, right? But how can you get rid of a square root in an equation? Square both sides. Exactly. Let's square both sides. And further, how should I proceed to solve this for x? Subtract x squared. So now we have 3x squared is equal to 25. And then take a square root of both sides. Technically plus or minus, but you only need the positive solution here. You can get a decimal if you like, or I can also do it like this. The square root of the top is 5. The square root of the bottom is root 3. I can also leave it like this. You could even multiply top and bottom by radical 3, but I'm not picky about rational as a denominator. That was, like I told you before, an old historical thing. It was easier to multiply with a radical than to divide before calculators, basically. It's okay to leave it like that. But let's just get a decimal as well. Roughly 2.89, right? 2.89 kilometers from that point A. We're saying that if you tie the connection, you go underground up to that point, and then from that point forward, you go above the ground, you should have the lowest possible cost to lay cable from that oil well to the desired point at the shore. I asked you to do one more thing on the problem. If you read the last few sentences in the problem, what did it ask you to do? It says, compare your answer with the cost that it would take to lay the pipe all on land or all underwater. Which estimate is the best? Now, the reason I'm asking you to do it this way is because I want you to check your answer somehow. To check your answer, you can either find a second derivative, but this one was pretty messy. Finding second derivative is going to be even messier. Or you have another choice. The other choice is compare the original function at the critical points and the endpoints of your interval. Okay? In this case, what are the endpoints of our interval? So x, you look at the picture once again. X can be, the lowest x can be is if you directly connect with the shore right away, then basically x is 0, right? The other alternative is you can go directly underground, underwater rather, all the way to here. In that case, what is what is x in that case? So you're connecting to the ground right here. You went this way. So then x is 8, right? Those are the two extreme situations. So your x is going to be, the lowest it can be 0. Oh, sorry, I forgot to switch my pen here. Okay, so the lowest is 0. The highest it can be is 8. So the lowest x can be 0. The highest x can be is 8 kilometers. Or the critical point we found is 2.89. So if you can check the original function you're maximizing or minimizing at the two endpoints of the domain as well as at the critical points, you can also determine which one is the absolute max, which one is the absolute minimum, right? Okay, now the cost function was a messy one. So the easiest way I would suggest that you do this one is put your cost function to your y1, and then go to your table, put 0, 2.89, and 8, quickly evaluate the cost function, at these 3 points. And the cost function was not C prime, but C, right? 1,000,000 times, so 1,000,000, I'm going to abbreviate it by 1m, times the square root of 25 plus x squared plus 500,000, abbreviate as 500k, times 8 minus x. Go ahead and enter this into your y equals screen. And then go to your table and enter these 3 numbers. Let's see what we get. If you plug in a 0, what did you get? If you plug in a 0 for x, what was the cost? You know, this represents, plugging a 0 for x represents the following situation. You go underground straight, you know, basically you cross the river or the water straight down, and you lay the cable underwater there, and then the rest of the way you go above the ground that way. That's what that first point represents, x equals 0. And how much is the cost in that situation? Roughly $9 million. I'm just going to say that 9 times 10 to the 6, $9 million. Okay, how about 2.89? What did you get there? Again, if you enter this to your Y1, it's the easiest way to do this. Of course, I abbreviated 1 million. You go ahead and put your entire million, you know, 500,000, put the whole number there, obviously. And anybody who got something that starts with an 8? Good, exactly. So that's $8.33 million, basically, times 10 to the 6, right? And the last one starts with a 9, I believe. $9.43 million. So which one is the absolute lowest point, absolute lowest cost for completing the job? This one right here, right? It saves you, you know, even from the other option, you know, almost like $670,000 cheaper if you use calculus to determine how far you should go on the land. Instead of going directly like this or directly like that, if you just decide where to connect the pipes and go some up below the water and some above the ground, that seems to be the best possible scenario with the lowest cost. So here we have another example on optimization, for which I'll give you a hint and ask you to try to complete it. Okay. So we're given that a rectangle is inscribed in a triangle. So the vertices of the rectangle basically needs to be on the triangle. So it has to touch, the corners of your rectangle must touch your triangle. And the base of the rectangle must lie along the base of your triangle. We know the dimensions of the triangle. It's 16 by 12. The question is, what are the dimensions of the rectangle that will give you the maximum possible area? For example, you could have a rectangle like this, right? This rectangle satisfies the condition. It does lie. The vertices are on the triangle. The bases on the shared together on the rectangle and triangle. But chances are this is not going to be your best one, right? This is not going to be your largest one. You could also do something like this. This one right here. Let me try a different color. This is also satisfies the conditions. The two end corners are on this triangle. The base is shared with the triangle. But this one is not going to be the one with the largest area either. Usually, it's neither extreme. It's somewhere in the middle usually, right? So our job is to find exactly what the dimensions should be. Which one of these, or another one, obviously, that will be the ultimate one, the best one. Okay, so let's assign some variables because we want to find the dimensions of our rectangle. So let's assign some variables for the dimensions. Now to make the problem a little bit easier, I'm going to call the height of the rectangle y. And you can call the base of this rectangle x if you like, but I think it's a little bit easier if I call this side x, and then what would be the base of the rectangle with that observation? 16 minus 2x. I'm going to write it outside. That is 16 minus 2x. So we're saying that the dimensions of the rectangle are 16 minus 2x by y. So when you find x and y, don't stop there. You got to come and find out what 16 minus 2x is, right? That will be the length of your rectangle. Does everybody agree with that? Okay. Now, how in the world could we somehow get x in terms of y? But before I mention that, you're trying to maximize the area, right? What is the area of this triangle? Base times side. The base is 16 minus 2x, and the height is y. Okay? So we have two variables. We need to write one in terms of the other. What kind of an equation do you think I could use here to write one in terms of the other? It's not the area, but it's the side length. 16 minus 2x is the side length of our rectangle, and y is the other side of our rectangle. It's not the area. But the area is the product of those two dimensions. Area is 16 minus 2x times y. So my question is, what kind of an equation can I use here in order to write x in terms of y? Any thoughts? I'm even going to give you a hint. Well, I heard the correct answer suggested. Somebody said it. How could we get x in terms of y? We know the outside dimensions of the big triangle, right? And this little one here has y as the height and x as the width of this triangle over here. I heard similar triangles. I heard the ratio. Same idea there, right? We can use similar triangles. Which triangles are going to be similar? The big one on the outside, this one, with the little one on the inside, which is this one. Okay, so let's try to set up now the ratios. Okay, on the big triangle, tell me what is the ratio of height to base on the big one. But we're talking about this big triangle on the outside. So the height is 12, and the base of that one is, this is half of the original triangle, which is 8, right? Okay, how about on this little one over here, the one outlined by red? That one is similar to the big one, right? So we did 12 to 8 on the big one. On the little one, we should say so many of you said y to x, because again, we had this one was 12 to 8, and this one is y to x. On the inside, it's y to x, basically. Okay, maybe I use another color to outline the two similar triangles. This is the outside one. That's the big triangle, but on that one, the ratio of 12 to 8 equals, on the little one, the ratio of y to x. Right? So there we have an equation. From this point forward, I think you're going to be able to finish this question. So this is where I'm going to stop, and we'll come back to it later. All right, let's go ahead and complete this question. Now that we have an equation that relates our variables x and y, and we also know what we are supposed to maximize, which is the area of the rectangle, which we had determined to be 16 minus 2x times y. Okay, first thing I'm going to do is go down here. Since 12x equals 8y, I'm going to get y in terms of x. Y is 12x over 8. Let's divide both sides by 4. So I get 3x over 2. So now I'm going to go back to the area equation and substitute that for y. Y is 3x over 2. So as always, before we differentiate, let's clean this up a little bit. Now I'm going to take out the 1/2 up front and then multiply 3x with both of these two terms. So I have 3 times 16, or 48x minus 6x squared. And now we're ready to differentiate it. I suppose we could distribute the 1/2 also to even simplify it further. You could do either way, either differentiate at that level, or since both of these two terms are divisible by 2, we can also leave it as 24x minus 3x squared. Okay, now I will go ahead and differentiate it. Set it equal to 0. So x is equal to 4. And what about the units? Everything was in terms of inches. Now remember that x is not one of the sides of our rectangle. Our rectangle was 16 minus 2x on one side and y on the other side. So now that we have x, let's also find out what is 16 minus 2x, which will be 8 inches. So that's one side of the rectangle, and the other side, which is y, which based on this was 3x over 2. And since x is 8, it'll be 24. Let's see. I'm sorry, x was 4. So y will be 3 times x, or 3 times 4 over 2, or 12 over 2. So that's going to be 6 inches. So the 8 inches is one side of the rectangle, and the other side is 6 inches. So the answer is the dimensions of the rectangle that will give us the largest possible rectangle that goes inside that given triangle. Those dimensions are 8 inches by 6 inches. So the base should be 8 based on our picture, and the height should be 6. So this, when inscribed in that triangle, will give us the largest possible area enclosed by a rectangle. How do we check the answer? Once again, take the second derivative of the area function. In this case, it's negative 6. It's always negative, meaning always concave down. So the point that we obtain, indeed, is a maximum for the area function.